So welcome to video 2 of this lesson on control of sodium and water excretion. This video will concentrate mostly on regulation of sodium, okay? So the regulation of sodium in your urine, again, that drives an awful lot of how much water you're going to retain. The regulation actually begins, although most of it, what we think of, happens in the collecting ducts. It actually begins in the proximal tubule through a process that we call pressure natriuresis. Now, you guys will remember most of the sodium is actually reabsorbed in the proximal tubule, and this pressure natriuresis, that is an increase in sodium excretion with blood pressure, is one way that you get rid of excess sodium. So an increase in blood pressure sort of implies that you might have an increase in blood volume. It certainly implies that you have an increase in pressure. One way to get pressure down, at least long term, is to get rid of some of the sodium and the water along with it. So pressure natriuresis, the first thing to remember is that a large part of this, though not all of it, is simply driven by hemodynamics. If you increase blood pressure, you increase pressure in the glomerular capillaries. If you increase pressure in the glomerular capillaries, you increase the amount of filtrate, and that means you increase the amount of sodium filtered. So simply by increasing the amount of sodium and water filtered, you're going to get some increase in sodium excretion through the urine. And so you'll get at least some loss of sodium that way, and therefore, ultimately, at least some loss of water as well. Okay, so that's the first thing to remember. And the second thing is down here in the bottom right-hand corner, and that is some of the nitty-gritty details which we really can't tell you about because nobody really knows a whole lot about them. But somehow, increased blood pressure causes a reduced sodium reabsorption in the proximal tubule, okay? And somehow is about all we can say about it right now. There is also a reduction in water reabsorption, and that should make some sense to you, because ultimately the amount of water reabsorbed is dependent upon the amount of water, just like in any other capillary in the body, the amount of water that you're filtering, that is, you're pushing out through hydrostatic pressure, relative to the amount of water that you're reabsorbing through osmolarity in the capillary and those retained proteins like albumin, which increase the osmotic pressure. So if you increase the blood pressure, that means you increase pressure in the peritubular capillaries, the hydrostatic pressure. If you increase the hydrostatic pressure in the capillaries, that means you increase filtration relative to reabsorption. So ultimately, you reabsorb less water in the proximal tubule simply because there's an increase in blood pressure. That makes sense. Increased capillary pressure should mean ultimately less reabsorption relative to filtration, okay? Because you're just increasing filtration. It makes less sense for sodium. Nobody really knows why you get reduced sodium reabsorption along with that, okay? But somehow it happens, and that contributes to this pressure natriuresis, where a high pressure in the capillaries will lead to more sodium retention in the tubules, less reabsorption in the capillaries, more left over in the tubules, and that leads to a natriuresis as well. So again, that happens in the proximal tubule. So this is a proximal tubule phenomenon. It's driven by hemodynamics. There are no sensors involved. It happens in an isolated kidney. And frankly, other than this hemodynamic component where you get more filtered and therefore, more in, therefore more out through the urine, other than that, nobody really understands it, to be perfectly honest. But somehow, increased blood pressure leads to less sodium reabsorption in the proximal tubule, and that leads to more sodium excretion as well. And that leads to more water loss and a drop in blood pressure ultimately. Okay? So that's the first part of our sodium balance and our sodium regulation. Okay, so let's look at another way that this pressure natriuresis helps regulate, well, ultimately blood pressure and GFR here. So here we have hemorrhage at the top of one of our summary slides here. And hemorrhage leads to a decreased afferent arterial pressure, as we said. That decreases glomerular hydrostatic pressure, and that decreases GFR, okay? And as you'll recall from the first lesson or two that we did in the renal section, that decreases delivery to sodium chloride to the macula densa. And so that causes an autoregulatory response where we get dilation of this afferent arteriole and an increase in GFR. So remember, we have the distal convoluted tubule coming up, and we have our afferent and efferent arterioles sort of like straddling it here. And we have our macula densa, which senses the sodium chloride in that area, and that induces our autoregulatory response. So that's part of maintaining GFR here. Well, another part of that response has to do with renin. So here we have the hemorrhage here, and here we have an increase in fluid reabsorption in the proximal nephron, the proximal tubule, okay? And this is related to our pressure natriuresis. So remember, when you have a decrease in blood pressure, you decrease the capillary hydrostatic pressure, and that causes less filtration. So less filtration relative to reabsorption means ultimately you're reabsorbing more net fluid in the peritubular capillaries around that proximal tubule. So when you get a drop in blood pressure, you get more fluid reabsorption in the proximal tubule, okay? And that also leads to decreased delivery of sodium chloride in the macula densa, okay? Because you decrease the flow of tubular fluid, so you get less sodium chloride delivery because you've got less fluid, okay? And so that also acts at the macula densa. And so we have our autoregulatory loop here. We also have our medium-term blood pressure regulation here, where you get a decrease in delivery of the sodium chloride to the macula densa. That causes release of prostaglandins, and prostaglandins cause an increase in renin secretion. Increased renin leads to increased angiotensin II through conversion of angiotensinogen, angiotensin I, and ultimately to angiotensin II, okay? So this is another branch of this response in the macula densa, okay? That this response to a decrease in blood pressure, you get this autoregulatory response, which tends to bring your GFR back up. And you also get this release of angiotensin, okay? Which will ultimately increase TPR and increase blood pressure, so that you'll bring blood pressure back up toward normal. And you'll also get a preferential vasoconstriction of the efferent arteriole, which will also help increase this GFR back toward normal, okay? So another role for the macula densa in our regulation of blood pressure and our regulation of GFR, okay? So that leads us to our long-term regulation, which has to do with regulating sodium and water, right? So the kidney controls renin release, we just talked about that, and it also controls blood volume by controlling the sodium. And as it says right here, if you control the sodium, you control the blood volume, because water moves with the osmolarity, and a good part of the osmolarity in your plasma is sodium related. So if you retain more sodium, you retain more water. And that's how you can control water movement, through control of sodium. Okay, so now let's take a look at aldosterone, which is our primary mechanism by which sodium is regulated in the plasma. And let's start, as we have on some other slides, with a drop in arterial blood pressure, let's say through hemorrhage, okay? And what this causes, again, as demonstrated on the last slide, is the release of renin. And renin leads to conversion of angiotensin I or angiotensinogen to angiotensin I, That leads to conversion of angiotensin 1 to angiotensin 2 because of angiotensin converting enzyme, okay? The increase in angiotensin 2, in addition to causing vasoconstriction, it acts on the adrenal cortex, okay? And it causes the adrenal cortex to release aldosterone. And aldosterone also acts on the kidney. So we're back to the kidney again here, where we increase sodium reabsorption in the kidney, okay? And that's through increasing the sodium channels in the apical membranes in your collecting duct, okay? And that increases sodium reabsorption, okay? As we've shown in the past, and as I'm going to show you in the next slide, okay? That leads to sodium retention, and that leads to water retention, because when you retain sodium, you're increasing the osmolarity, water follows the sodium, and you get conservation of water, which will help bring your blood volume back up, help bring your blood pressure back up, okay? So ADH is our primary sodium regulator, okay? It acts by increasing the number of apical channels in the collecting duct, and it also increases the sodium-potassium ATPase activity in the basolateral membrane, which means you're transferring more sodium out of the cell and into the interstitium. So it helps keep that sodium concentration extra low in the cell so that you can continue to reabsorb more sodium. Okay, so that helps sodium reabsorption as well. And do note that ADH and aldosterone act synergistically, okay, to regulate water, okay? They both have an effect, you know, aldosterone through the sodium, ADH directly through water permeability, as I'm going to show you in the next video, okay? And they act synergistically to regulate water excretion. Also, you should note the effect of atrial natriuretic peptide, as the name implies, natriuresis, right? So once again, we have an increase in arterial blood volume, and this leads to stretch of the atria and the release of atrial natriuretic peptide. And that, first of all, causes vasodilation, and in particular it causes vasodilation of your afferent arteriole, which increases GFR, and that increases sodium and water filtered, and that will increase the sodium in your urine, okay? So that is step one. You have this vascular effect of atrial natriuretic peptide, and that's part of the way that it causes natriuresis. The other part is by increasing sodium reabsorption in the kidney tubules, okay? And it does that, and so that increases sodium excretion in urine. In addition, so it decreases sodium reabsorption in the kidney tubules, and it inhibits the renin-angiotensin-aldosterone system. And again, this is how aldosterone works. It acts to increase these sodium channels in the apical membrane. It also acts to increase the sodium-potassium pump. So if you inhibit that, you actually decrease sodium reabsorption, and so you get more sodium in the urine, and water follows osmotically, and you get rid of sodium and water. So you get a natriuresis due to the release of atrial natriuretic peptide, due to direct effects on smooth muscle, and the vasodilation that you get, and also to the inhibitory effects on sodium reabsorption and on the renin-angiotensin-aldosterone system, okay? Okay. So that brings us to regulation of water excretion in the kidney, so I'm going to stop there, and we'll take care of that in the next video. Thank you.